Hypothesis test for population variance. Now the process for a hypothesis test is the same for variance and population mean. So we follow the same 4 steps that we've seen in the previous modules. The first step is to state the hypothesis. So there's the null statement and the alternative statement. So if we reject the null statement, then we accept the alternative statement. The second step is to state the level of significance. Now this usually will be given. So just for example, if the level of significance is 5%, that would be an indication that we want to give the null a 95% confidence interval. And why do you want to give the null such a wide confidence interval or an acceptance range? Because we're going to be using a sample in order to test for the population variance, and samples have errors. So that's why we want to build a margin of error around the null statement. Now the third step is to identify the distribution for the variable that we are testing. So in this case, we're going to be looking at variance. So when it comes to variance, there's only 2 choices on the menu. It's either chi or f-test. And if it's a single population, then we use chi. And that's why I've circled it in red. And then step 4, we do the test. Now, the test for a hypothesis is really akin to penalty kicks. Now, the way penalty kicks work is as follows. So here's your net. And if the ball comes anywhere within the net, it's a goal. But if the ball goes outside the net, then it's not a goal. What's that got to do with hypothesis testing? Well, with hypothesis testing, here's the null. Right, it's right in the middle. And what we do is we build a confidence interval around the null. So that's why we have these goalposts. Now, if the sample comes anywhere within these goalposts, then we accept the null. But if the sample falls anywhere outside of these goalposts, then we reject the null. So that's why I always liken a hypothesis test to penalty kicks. And I use the same terminology. For example, the first thing we need is the goalposts. That's these things right here. And to identify the goalposts, we need to specify the degrees of freedom, which is n-1. And we also need to specify the area of the right side. And we'll show this when we do an example. Now, I call these goalposts because in the back of my head, I'm thinking penalty kicks when I'm doing hypothesis tests, but really the proper term for them is critical values. So goalposts, these things right here, they're your critical values. And then the sample stat would be the ball itself. And with the sample stat, when it comes to testing for variance, may be found as follows. So we look at n-1, which is the degrees of freedom right there, and we multiply it by the ratio of the sample variance divided by the hypothesized variance. And that's the thing, ladies and gentlemen, when we're doing a hypothesis test for a variance, it means that there's a claim being made about the population variance. So then the question is, does the sample variance support the claim about the population, or does it refute the claim about the population? So now we're ready for our example. Let's have a look. A mutual fund claims that the standard deviation of their performance is less than 9%. And again, remember, standard deviation represents the dispersion of individual returns around the mean. So it's a measure of risk. Okay. To test this hypothesis, the analyst draws a sample, and in the sample there's 60 monthly observations. So that's 12 months times 5 years. So that's where you get 60 months worth of return data. And the standard deviation of those 60 observations was 11%. Now, can I ask you a question? Why can't we just reject the null right off the bat? Why can't we just stop the analysis right there? Because the claim was, there it is, the claim was that the standard deviation is less than 9, but the sample was 11. So 11 is greater than 9, so why can't we just reject it? Because that 11% was based on a sample, and samples have errors. So you got to build a little margin of error around this null hypothesis to account for that sampling error. So that's the whole point of hypothesis tests. So let's go through the steps. So step 1, state the hypothesis. Now, from a previous module, I indicated that if the hypothesis contains an inequality, such as a greater than or less than sign, we make it the alternative. So I went into the whole discussion in the previous module, so you can follow up on it if you like from a previous module. But here I want to keep it simple. If you see an inequality, you make it the alternative. So therefore, and the second thing we need to be mindful of is that when you're testing for volatility, the test is specifically based on variance and not standard deviation. So those are the two adjustments we need to make to this hypothesis. So here we go. First of all, here's the hypothesis, but because it contains an inequality, you said make it the alternative. Done. I made it the alternative. And what's the second thing we need to be mindful of? This test is regarding variance and not standard deviation. Done. And that's it. That's it. So that's your alternative. Now, the alternative and the null are complements to each other. So if the alternative says that the variance is less than 9 squared, then the null would say that the variance is greater than or equal to 9%. So you see that they are mutually exhaustive. In other words, they're complete complements of each other. It's either one or the other. There's nothing in between. All right. Step 2, level of significance, 5%. Again, as I said, this will be given. So what is the significance of this 5%? That means we want to give the null statement a 95% confidence width or an acceptance width. Step 3, what's the distribution for variance? So how's the variance distributed? We use the chi distribution. And then step 4, we do the test, which is very much like a penalty kick, right? So first, let's work on the goalposts. And here it is. So how do we set up the goalposts? Because this is going to be a one-tailed test. How do I know it's a one-tailed test? Because if you look at the null, we're only interested in one side of the distribution. It says null is all values greater than 9 squared. So let me ask you this. If I had positive infinity, would that be null range or alternative range? Well, let's see. Positive infinity, last time I checked, positive infinity is definitely greater than 9 squared, so that would be null territory. So that's my clue that the null range starts from positive infinity and goes all the way to the left side of the distribution. So the entire 95% acceptance range for the null would be on the right side. So positioning the goalpost is very, very important. And that's how we sort of trick. That's the trick we use to figure out where the goalpost lies. So the goalpost is going to be here. So then if we know that this 95% is null territory, then this tail area on the left side would be alternative territory. So you can see why I use a penalty kick analogy, ladies and gentlemen. If the sample comes in anywhere here, that's null territory. On the other hand, if the sample comes anywhere here, that's alternative territory. So now we're going to figure out where the goalpost will lie. So the first thing we need to figure out is the critical value. So where does it lie? And to get the critical value, we need to go to the tables. And we're going to be looking for two things. The degree of freedom, which is n-1. So in this case, that works out to 60 minus 1, which is 59. And we need to specify the right side area. So if you look at this distribution, the right side area, so that's the right side, that's the left side, but the table only asks for the right side. In this case, it's 0.95. Now, I should point out what it is that we're plotting on the horizontal axis. So what are we plotting here? It's this over here. So therefore, what's the expected value of this distribution? Well, the expected value, what do we expect? What is our default expectation? Our default expectation is that the sample variance will equal to the hypothesized variance, unless proven otherwise. So if these two are equal, this ratio will equal to 1. Therefore, the expected value of this distribution would just be equal to n minus 1. So now what we're going to do, of course, is we're going to see where the goalpost lies on this distribution and where the sample lies on this distribution. So first, getting back to finding where the goalpost lies. Again, degree of freedom 59, right side area 0.95. So now I'm going to take you to the chi table and see where the goalpost will lie. And here we are. So this is the chi table. And notice it asks for the degrees of freedom and the level of significance. So here it is. The level of significance was 5%, so it led to a probability in the right tail of 95. And the degree of freedom was 59, so the closest value we find is 60. So if we triangulate, so degrees of freedom and probability on the right tail, we triangulate to 43.188. So that's where we got that number. So this would be our goalpost. And by the way, what would be the lowest value in this distribution? You could see that it's skewed, because when it comes to variance, ladies and gentlemen, variance cannot be negative. So you don't see this left tail going all the way to negative infinity. In fact, the lowest value we can have for the horizontal axes would be what? Let's see. Well, what if the sample variance was 0? Then the whole term would be 0. And that's why you actually do have a finite point on the left side of this distribution. So think of this as 0, and then the goalpost would be right here. So it's 43.188. So the only question now is, did the ball come within the null range, or did it go outside the null range? And that's where we have to find the sample statistic. So let's go have a look and compute it. So here's the sample stat framework. It's the same thing as there. So that's the actual distribution. So we just plug in the values. So n minus 1 is 60 minus 1. The sample variance was 11 squared. And that's also where you have to be careful, ladies and gentlemen. The data was given to us in standard deviation format. But these hypothesis tests for variance is always looking for the variance, i.e. the square. And the hypothesized value was 9 squared. So therefore, the sample statistic would be 88.14. So let's go and position this 88.14. Let's see here. If this point here is 0 and the goalpost is 43.188, therefore the 88 must fall somewhere in there. So i.e. it's going to be on the right side of the goalpost. And then when you look up, you say, oh, that is null territory. So what's the decision rule? Here we go. The sample stat was within null range, so therefore you accept the null. In other words, it's possible that the standard deviation is greater than 9. And I just wanted to show you where that came from. Remember, ladies and gentlemen, the hypothesis test is centered around the null. So if you accepted the null, you accepted the statement, i.e. the variance is greater than or equal to 9, or alternatively, you could say standard deviation is greater than or equal to, variance is greater than or equal to 9 squared, which translates to standard deviation is greater than or equal to 9%. So if it's possible that the standard deviation is greater than 9, then there's no conclusive evidence that it's less than 9. You cannot say that conclusively it's less than 9 when at the same time you're telling me, oh, it's possible that it could be greater than 9. So it's got to make sense. And how confident are you in this conclusion? We are 95% confident in this decision. Or the other way it's expressed, we reach this conclusion at the 5% level of significance. Because when you're making statements without knowing the population value, you have to indicate how certain you are in that statement, because it's not an absolute statement, because we don't know what the population variance is. So when you make a claim like this, you have to indicate your level of certainty. So in this case, it's at the 5% level of significance, which translates to being 95% confident in that statement.